All right. It is 3:30. We can go ahead and get started. Let me just make sure. Okay, good. I am recording. Okay, cool. Let's talk about a couple of announcements before getting started. Yeah, so basically we are in the final descent of the end of semesters. I don't know about you guys, but I'm definitely looking forward to it. This week is going to be our final week of new content. What we're going to do is start and complete Unit 14, which is going to be about mini batch k-means. And then hopefully we'll be able to complete all the things that we'll need to talk about for Unit 15, which is spectral clustering. Now, unfortunately, in order to, I guess, ensure that we get through the testable content, I guess you could say, in these two units. For Unit 14 and Unit 15, there are Jupyter notebooks that show you how to essentially use scikit-learn to implement these two algorithms that we're going to be teaching you. Unfortunately, in the interest of time, we're running out of time in this particular class. We won't have time to actually get to the actual code implementation of these algorithms. But those Jupyter notebooks are there if you'd like to, go through those notebooks and, essentially learn how to implement the algorithms. But essentially, what we're just going to be focusing on here in this final week is how these two clustering algorithms work. And that is content that you will be tested on. So there are questions about Birch, mini batch k-means, and spectral clustering, which do make an appearance in the practice test materials that I released. So I would say, if you want to gain practice with this new content, definitely, put a lot of focus on that material. Yeah, and then regards to, additional prep or help that you might, need in, prepping for that exam. Um, I do have my, my Thursday, excuse me, my Friday office hours this week. Um, if you guys wanted this, I could also host some office hours on Sunday as well. However, unfortunately, on Monday, I will be flying to Champaign, so I'll be mostly unavailable on Monday for any last minute questions, at least in person. So I think what I'll do is I'll release a poll just kind of asking if you guys want additional office hours for that Sunday, which is something that I'm willing to provide. But yeah, otherwise, after that, we'll take that exam. We'll have some additional time to work on the group project. So we'll be presenting that in person on May 8th. I'll probably be hosting some additional office hours to, help you guys answer any last minute questions that you might have about that group project. So I'll probably let's see, May 8th is a Wednesday, so I'll probably have office hours on that Tuesday as well as the Friday before that as well. Yeah, and I think that's about it. So we make sure that you're declaring your group. I think I set the deadline for group declaration to be Thursday. So again, if you're having any issues, finding group members, definitely feel free to reach out. If I see that you're not a part of a group by the 25th, I'll probably be reaching out to you just to kind of ensure that you're working with somebody. But yeah, I think that's basically it. So I'll be proctoring the exam in person on Tuesday, so I will see you guys in person. But yeah, and then also make sure that you're making your cheat sheet if that's something that you want to do, but do make sure that it meets all of the correct specifications. So it should be again handwritten front and back if you'd like on a regular size piece of paper, and you can't have anything like computer printed on that. Otherwise, it won't be able to be used essentially. But yeah, I think that's basically it. So yeah, any questions before we get started? Okay. All right, so what we're going to talk about today is another online clustering algorithm that we call mini batch k-means. So we just discussed another online clustering algorithm known as Birch. And again, the reason why Birch, as well as mini batch k-means, is what we call an online clustering algorithm is because we don't actually need to have or use the full data set at any one given time to cluster that full data set. Rather, each of these online clustering algorithms that we're going to introduce only require a portion of the data set. And then basically the clustering structure of the full data set is iteratively updated as we feed in observations into the algorithm. So you might have noticed this already when we were discussing BIRCH, but it did take a long time to essentially talk about like how BIRCH actually works. So from the perspective of a data scientist trying to cluster a given data set and trust the results of that cluster analysis, what might be a particular downside to the BIRCH clustering algorithm? So the question is a lot of parameters to tune. Hold on one second. So I would say there's not too many comparatively parameters to tune. So we have the diameter or the radius threshold, which is actually something that the extended phase 1 can actually tune itself with. And then there's also the number of nodes or the number of entries that you allow on each of your nodes. But basically after that, those are pretty much the main parameters that we need to think about when tuning, at the very least when we're using the scikit-learn version of BIRCH. But maybe it's just a little bit more straightforward. I mean, personally, I find the fact that it took me like way longer to actually explain how the BIRCH clustering algorithm works, is one way in which we might say that the algorithm is not as explainable. Right. So we looked at like, how the BIRCH clustering algorithm actually works. It's like basically 2 pages of like all these complicated steps. So the BIRCH clustering algorithm is very powerful and it's very cool because it actually implements and considers your memory constraints when, finding or determining the clustering structure of your data set. But, if your goal is to, essentially build trust with your boss or whoever is using the results of your clustering algorithm, well, unfortunately, a downside is that BIRCH is not as explainable. So therefore, another commonly used online clustering algorithm that is considered to be a lot more explainable is the mini batch k-means clustering algorithm. And as the name might suggest, it actually does look very similar to the regular k-means clustering algorithm. But as the mini batch part suggests, rather than feeding in the entire data set into the clustering algorithm, we actually only need to feed in what we call mini batches, or essentially random samples of the full data set into your clustering algorithm at any given time. So another benefit that this mini batch k-means clustering algorithm has over the regular k-means is that it has a much better computational complexity than k-means. The computational complexity of k-means is in order of the number of objects, attributes, clusters, and iterations. However, the computational complexity of mini batch k-means is actually going to be a lot smaller than that. And then also, one of the downsides of k-means, like we saw, is that, we need to have that full data set or the full data set in our computational working environment at any given time. So it's not going to be the case for mini batch k-means. Actually, the only thing that we need in our Jupyter Notebook or computational working environment at any given time is simply just a random sample of the full data set. So the way that the mini batch k-means clustering algorithm works is as follows. And so I think what I'd like to do is I'd actually like to go through these steps as I'm clustering a small data set. But the bullet point is the input for the mini batch k-means clustering algorithm is a data set comprised of m objects with n, and this is key, numerical attributes So just like we saw with k-means, in which we should really only be clustering numerical data sets, the same thing is going to hold for mini-batch k-means. And then furthermore, we're going to talk about this a little bit later, but a lot of the same types of data sets that k-means is best designed to detect the clusters in is also going to hold for mini-batch k-means as well. Okay. Now also, just like in k-means, we do need to pre-specify the number of clusters that we're looking for. Okay. Now, given that we're running mini-batch k-means, there's actually two additional parameters that we would need to pre-select. So this is B, our mini-batch size, or in other words, how large of a random sample from the full data set do you want to feed in to a given iteration of the algorithm? And then furthermore, there's not necessarily any preset stopping condition for mini-batch k-means. It's simply just a question of how many iterations would you like to go through in order for you to feel satisfied with the clustering structure that has been detected so far in the algorithm. Okay, so basically the mini-batch k-means clustering algorithm works somewhat similarly to k-means in that we, generally speaking, have this centroid initialization step, although the way that we initialize our centroid is going to be slightly different. And then furthermore, we're also going to iterate through a cluster assignment step, as well as a centroid update step in each iteration of our algorithm, much like k-means. But there is going to be some slight variation as well here. Okay. So let's just say, for instance, this data set here is our full data set that we would eventually like to cluster. It's just comprised of 5 observations. But let's just say, for instance, that, a data set with 5 observations is too large to, load at any one given time in our Jupyter notebook. So what we might like to do instead is say, well, okay, let's, rather than load the full data set into our Jupyter notebook at any given time, let's load in a series of mini batches or random samples from that full data set. Now let's, for instance, select our mini batch size to be 3. So basically each of our mini batches are going to be random samples of 3 observations from the full data set. So our centroid initialization step does require us to initialize k centroids for the algorithm. However, in opposition, or as opposed to k-means, which simply just randomly selects our centroids within a certain range of values, the mini-batch k-means clustering algorithm requires us to actually randomly select 2 observations from our actual data set. So for instance, let's just say we randomly selected the point 1, 1 as our first centroid, and we randomly selected the point 1, 14 as our second centroid. So, shoot. This would be our first centroid here. And this would be our second centroid here. Okay. Now, also in our initialization step, there's another object that we didn't have in k-means that we need to initialize here as well. So for each of our k centroids that we are updating in the mini-batch k-means clustering algorithm, each of these centroids has essentially a count, or a tally, if you will, which counts up the number of observations in the data set which have currently been assigned to that particular centroid. So we randomly initialize the observation count for these 2 centroids to be 0, otherwise indicating that we have not actually assigned any observations to these 2 centroids yet. Okay, so that is our initialization step. Okay. And so the second step basically goes through T iterations, where T is the number of iterations that we pre-specified ahead of time. And so the first thing that it does in a given iteration is it randomly samples a mini batch. So we will randomly sample our first mini batch with 3 observations. The mini batch here. And so once we've randomly sampled the mini batch, these observations here, what we do is we assign each point to its closest centroid. This is very much like what we have done with k-means. Okay, so this observation gets assigned to this point. These 2 observations get assigned to this centroid. Okay. And so therefore, at the moment, we have come up with a tentative cluster assignment for just 3 observations in our full data set. So this is assigned to centroid 1. This is assigned to centroid 2. And this is assigned to centroid 1. Okay. And so as of right now, because these observations here are not in the current mini batch, their cluster assignment has yet to be specified. Okay. All right, so that is our batch cluster assignment step. Oh crap. Second. Okay. All right, so once we have assigned each of the observations in our batch to their closest centroid, then we engage in the centroid update step. Now, this is also going to be slightly different than what we saw in k-means. So what we do is we iterate, or basically we form the following steps for each of our observations in the mini batch, one at a time. All right, so I'm going to start with observation 1 in the mini batch. So observation 1, 1. Okay. And so we saw that observation 1 was assigned to centroid 1. So basically what that means is that we will use this observation to update its corresponding centroid that it's been assigned to. So what we do first is we take the tally of that corresponding centroid and we update it by 1. So therefore, we are indicating that this centroid now has had 1 observation assigned to it. Okay. Now, the way that the centroid is updated in mini batch k-means is actually based, somewhat based on a gradient descent type of algorithm. So in a given gradient descent algorithm, we are essentially updating the current or the old version of a given attribute to a new version of that given attribute based on some sort of learning parameter. So what we do is we calculate the learning rate for the given cluster update equation that we're about to use. So the learning rate that we use in the cluster update step for a given observation in our mini batch is going to be 1 over the current tally count of that corresponding centroid. So 1 observation has been assigned to centroid 1. So basically its learning rate is going to be 1. Okay, and so the final step in the centroid update step that corresponds to this observation is to recalculate the centroid that it was assigned to. So therefore, the new centroid 1 would be 1 minus the learning rate times the old centroid, which is 1, 1, plus the learning rate times the current observation that we're considering. And so it just so happens that our old centroid is actually equal to the new centroid, but that's not always going to be the case. Okay, there's really nothing that we need to update at the moment. So the old centroid is simply just now or the new centroid is exactly equal to the old centroid. Okay. So we've gone through observation 1 in the mini batch. Then we move on to object 2 in the mini batch, so 114. All right. And so we see that this observation was assigned to centroid 2. So therefore, what that means is that we're going to apply a cluster update step to centroid 2. But before we do that, first thing that we need to do is we need to update the tally for that corresponding centroid. So therefore, we update the tally for centroid 2. And so now we're indicating that 1 observation has currently been assigned to centroid 2. And then we calculate the learning rate we're going to use in the cluster update equation. Okay. And so the learning rate in this case is also going to be 1 over 1 because only basically this is this value here. So similarly, our learning rate is also going to be 1 in this cluster update step. Okay, so therefore, when we update our centroid 2 in our cluster update step, what we get is 1 minus 1 times our old centroid, which is 114, plus 1 times the current point that we're considering, which is also 114. And so it also just so happens that our new centroid is also simply just going to be equal to the old centroid. Okay, so not much has changed, so there's nothing that we would really need to update here. Okay. However, as we move on to the final observation in our mini batch, so 2, 2, we are going to see some change. Okay, so we see that 2, 2 was also assigned to centroid 1. So what we would do first is we would update the tally for centroid 1. We would update that here, now indicating that 2 observations have been assigned to centroid 1. And then we recalculate the learning rate that we're going to use in the corresponding cluster update step. Now in this case, the learning rate is going to be 1 over 2. Okay. So therefore, when we update, in this case, centroid 1, in our cluster update step, what we're going to get is 1 minus 1/2 times the old centroid, which is 1, 1, plus 1/2 times the current point in the mini batch that we're considering, so 2, 2. All right. So what we get is a new centroid location of 1.5 and 1.5. Okay. Right. So therefore, we would update the current centroid 1 to be 1.5 and 1.5. So someone's asking, can you go over why object 3 and object 5 are not assigned to any centers? Yeah, so that's correct. So they, unfortunately, they're not in our current mini batch that we're considering. So we don't have any information at all about object 3 and object 5 yet. However, when we move on to iteration 2, so basically this completes iteration 1 of the second step of mini batch k-means. And so when we move on to the next iteration, we're going to select a new mini batch or a new random sample. And so take note, now we have object 3 in this mini batch. So basically that is going to allow us to assign a cluster label to object 3. Okay, so for good measure, we'll go through one more iteration as well. So iteration 2, we have our new mini batch. These are the current 3 observations from the full data set that we have. And so what we would do is go through each of these 3 observations in the mini batch and update the corresponding centroids accordingly. So very quickly, observation 114, that's the first observation in the mini batch. And we see that that was assigned to centroid 2. Okay. So therefore, we're going to update the tally for centroid 2 to be 3 now. All right. Therefore, our learning rate now is going to be 1/3. Okay. And so therefore, we're going to update cluster 2 as follows. So we have 1 minus 1/3 times our current centroid 1 value, which is 1.5, 1.5, plus 1/3 times the current point that we are considering. Oh, my bad. Shoot, sorry about that. Should have highlighted that to be purple. That's centroid 2. All right. That should have actually stayed at 2. We should have actually updated this value to be 2. Yeah, sorry about that. So that would mean that, yeah, our actual learning update rate would be 1/2. So our cluster update step would be 1 minus 1/2 times centroid 2, excuse me, which is 114, plus 1/2 times the current point that we are considering, also happens to be 114. And so, just so happens, yet again, our centroid 2 has, in fact, not moved. It's simply just the same centroid that we saw before. So this here, so nothing needs to change. Okay. I think go through these 2 more steps. Okay, so object 3 is now, excuse me, the next observation in the mini batch. And so we assign that to centroid 1. And so we update centroid 1's tally. Now this would be 3. Okay, so therefore the learning update, the learning rate would be 1/3. And so when we update centroid 1 in our update equation, we get the following. One minus 1/3 times our current centroid 1 value, which is 1.5, plus 1/3 times the current point that we are considering, which is 5.5. So we get the new centroid 1 location to be 2.67, 2.67. So what we would do is we would update our centroid 1 to be that value. All right. And for good measure, let's go through the final part for step 2 of iteration 2. In other words, we incorporate the final observation in the mini batch. So we see that observation 2.2 was also assigned to centroid 1. All right. And so we update the tally for centroid 1. So now centroid 1 now has 4 observations that have been assigned to it. Okay. And the learning rate that we're going to use now is going to be 1/4. And so we update our centroid 1 as follows. So the new centroid 1 location is going to be 1 minus 1/4 times the old centroid location, which was 2.67, 2.67, plus 1/4 times the current observation that we're considering, so 2.2. So we get a new centroid 1 location to be 2.5 and 2.5. Shoot. Okay. And so we would update our centroid 1 location accordingly. Okay. Now, actually, I forgot to mention this, but there's before the centroid update step in each iteration of your algorithm, there's also the actual cluster assignment step. So actually, each of the each of these observations here would have been assigned to their closest centroid location. So basically, the centroids that we ended up with at the end of iteration 1 were these values here. So basically, before going into the centroid update step, what we would have done is first assign those mini batch observations to the current centroid locations. Okay. So by the end of the second iteration, our old centroid 2 is actually equal to the same location as the new centroid 2 value. However, you can see that our old centroid 1 value is actually in a different place as the new centroid 1 value. So now it's at the place, now it's at the point 2.5, 2.5. Okay. So what that means is basically in our batch cluster assignment step, this also, this allowed for object 3 to be assigned to an actual centroid, so centroid 1. And it's also the case that object 4, as well as object 1 and 2, remained also, closer to centroid 1 than centroid 2. So their centroid assignment did not change. But do take note that, it is possible for a given observation to be assigned to one centroid in a given iteration and then be assigned to another centroid in another iteration. So basically, our cluster assignments are not locked in place. It is possible for us to change. Now, let's just say, for instance, we only wanted to go through 2 iterations. In other words, only give ourselves the chance to only feed in 2 random samples of the full data set. So take note that if we'd only run 2 iterations of mini batch k-means, then observation 5 actually did not appear in any of our mini batches. So therefore, it did not actually receive the opportunity to be assigned to a given centroid in the data set. So therefore, going through just the initial mini batch k-means clustering algorithm doesn't necessarily actually assign it doesn't necessarily assign each observation to a given centroid. So therefore, what you can do is after you have gone through a sufficient number of iterations in mini batch k-means, what you can do is actually, feed in every single one of your observations from the full data set and assign it to its closest centroid that you have settled on after you have gone through each of the iterations in mini batch k-means. So for instance, where we left off at the end of iteration 2 was that our centroid 2 was here. And our centroid 1 Its final location was here, so 2.5, 2.5. So therefore, we would read in every single one of these observations from the full data set again and assign it to its closest centroid. This would be our final cluster assignment. Okay. So I'm seeing a private question, which is asking, does it matter which object you do first, or do you get the same centroid at the end of the iteration either way? So the order does matter. And so generally speaking, just for implementation purposes, we typically just start from the first observation in the data set and we work our way down. But the ordering of your data set does in fact matter. Yeah. So for instance, like if you had started with like this observation first, you might have gotten a different answer basically. Okay, but the idea here is, basically if you go through enough iterations or enough, if you go through enough random samples, you should generally speaking, your centroids should generally speaking end up roughly in the same location, regardless of what order you had used in the update process, essentially. Well, that's a good question. Any questions on that? Right. So let's think about, what's happening to our centroids, the more iterations that we go through, or in other words, the higher a given centroid's tally becomes. So generally speaking, we initialize each centroid's tally to be 0. And then as we move through each iteration of the algorithm, presumably more and more observations are assigned to a particular centroid. So basically the tally of that centroid tends to increase. So we want to think about what's going to happen to the resulting, or what happens to the resulting centroid when our tally for that centroid is currently at a lower value. So that is the question. Let me ask a poll. So the question is, if your tally for a given centroid is small, then what do we think our cluster centroid will move closer to in the cluster update step? So is it the point that we're currently considering? Or is it the old centroid location? Okay, so try to submit in the next few seconds. Okay, so why did I clear it? All right. Okay, so slight majority say number one, it's the centroid is going to move closer towards the current point that we're considering. So that is correct. So what you want to remember is, the lower this centroid tally is, then the higher this learning rate parameter is going to be. So therefore, the new centroid is going to look closer, or it's going to move more in the direction of this value, the current point that you're considering, than this value here. So for instance, like if your if you'd only assigned one observation to that centroid, then your gamma would be 1, right? And so basically your centroid would not move in any direction. So basically this would be a 0 here. So like the old centroid location would not be considered. But basically your new centroid would be exactly equal to the current point that you're considering. So what that means is that when your centroid tally is small, or in other words, you are earlier on in the algorithm, what that means is that your current cluster centroid will move closer to the current point that you are considering, which means that your centroids will be more flexible to new observations that are assigned to it. On the other hand, as you progress through more iterations in the algorithm, presumably more observations are going to be assigned to a particular centroid. So your centroid tally is going to increase. And so therefore, what that means is that your corresponding gamma value is going to decrease. So therefore, in the cluster update step, your centroid is going to move closer in the direction of the old centroid location. And so what that means is that as your centroid count increases, your centroids are going to become less flexible to new observations that are assigned to it. Or in other words, the centroid locations become more locked in place. Okay. Any questions on that? Okay, so this is the main general implementation of mini batch k-means. Now, oftentimes, one of the assumptions of how we run mini batch k-means is not necessarily met, practically speaking, or generally speaking, if your goal is to iteratively update a given online clustering algorithm with a set of like essentially new information as it's coming in, one of these assumptions of the mini batch k-means becomes much more impractical, if you will. So let's consider, the following, slightly more practical application of, how we might want to use mini batch k-means. So for instance, suppose that you'd like to cluster the responses of Twitter users from all over the world as they react to some global news story. And so let's just say the story was released at 9 a.m. Central Standard Time. And so here's what we'd like to do. Now, this is not the intended use case of mini batch k-means, but nonetheless, let's suppose this is how we want to use mini batch k-means. So suppose we'd like to use mini batch k-means to start clustering the data as these Twitter responses come in, rather than waiting a full 24 hours to cluster data from the full 24 hours of responses, if you will. So given the way that we would like to use mini batch k-means here, which assumption of mini batch k-means might be difficult to meet in this scenario? So let's just say, for instance, we decided that like a batch, like one of our batches that we wanted to incorporate was the responses from like the first 8 hours of people who had responded. And then maybe the next batch was the Twitter responses of people over the next 8 hours who had commented on that global news. So if these were like our batches, do you think that all of the mini batch k-means assumptions about, essentially about how the algorithm runs are met if this is how we were designing our batches? So you could say yes or no. Yeah, so someone's saying each iteration may not consider the same data in each choice of batches. Yeah, so it's not even just the same data, but like, I mean, technically it's okay if it's, if each batch is not comprised of the same data set. I mean, generally speaking, that's what we essentially want. We want each of our batches to be relatively distinct subsets of the full data set. But let's just say, for instance, I mean, so this piece of news, like it came out at 9 a.m. Central Standard Time. So what that means is that the people who were reacting to this, this news article, only a certain portion of people around the world were actually awake to wake up and read this news. So, you know, it could be that the first batch of people who react to this piece of Twitter news might be like people from like North America and South America, for instance. And then it could be the next batch of people to wake up and start reacting to this piece of news, or people who are making tweets about this piece of news between 5 p.m. and 1 a.m. Central Standard Time, might be in like Asia or Oceania. Furthermore, the next batch of people to wake up and start making comments about this particular news article, between 1 a.m. and 9 a.m. Central Standard Time might be people in Europe and Africa. Now, that's not necessarily a bad thing that like people are coming from different countries and responding. However, if there's different attributes to the nature of the batches, in batch 1, batch 2, and batch 3, then essentially one of our primary assumptions about how many batch k-means works is not essentially going to be met anymore. So in other words, if the batches are not random samples, or basically if the batches are not representative of the full data set that we would like to cluster, then the assumption that our batches are random samples from the full data set is not a valid assumption to make. Now, this is going to be problematic in a situation like this due to the nature of how our centroids can essentially become locked in place as we move through more iterations of the algorithm. So this unrepresentative set of batches may lead to worse overall clustering performance. Okay, so the bullet point is if you use mini batch k-means in the way that it was intended, in which each of your mini batches are random samples of the full population, then generally speaking, your mini batch k-means clustering will give you a relatively good clustering of the data set, provided it's the right type of data set to use with mini batch k-means. So like spherical clusters, clusters of equal sparsity, so on and so forth. However, the thing is, if you want to use mini batch k-means in a slightly more general way, where you're not necessarily assuming that each of your batches are random samples, then that overall can lead to worse performance of the, when it comes to clustering the data set. Now we're going to talk about a workaround for this worse performance in just a second, but just to kind of showcase how and why this might work, let's first go through this example here with the basic mini batch k-means, where each of our batches are not, in fact, random samples of the full data set, but rather they are unrepresentative samples, as we can see here. So let's just say we have the first batch that comes in. So basically people mostly who are showing up in this overall cluster here. And so we would randomly initialize our centroids to be simply just observations in this first batch. Now, the nice thing is, because we are starting the algorithm out, our centroid tally for each of our 3 centroids in this case, the centroid tallies are still relatively low. So therefore, what that means is that my centroid locations are going to be much more adaptive to change. Or in other words, when I apply this cluster update step, my centroids are going to much more flexibly move in the direction of the current points in the batch that we're considering. So even if these centroids were initially started out in a pretty terrible location with respect to this batch, they have much more flexibility to move to better locations. That's going to give us a much better clustering structure identification. However, as we move on to the second batch, what's going to happen is basically each of these new observations in the second batch, they're going to be assigned basically to this centroid 3. So centroid 3 is going to have a much larger tally of observations that are assigned to it. And because of that, when we apply the cluster update step, this centroid 3 is going to become much more locked in place to the previous location of it. So it's going to have much less of a capability to actually move into the direction of the points that have newly been assigned to it. And then it's going to get even worse as we incorporate the third batch. So now we have observations which are mostly over here. So these observations, again, are going to be assigned to centroid 3, but now the centroid 3 tally is increasing even higher. So what that means is that that centroid 3 location is becoming even less capable of moving in the direction of the observations that have been assigned to it. So therefore, overall, because we are violating the random sample assumption of each of the mini batches, our overall clustering of the data is going to be pretty poor, right? Because we didn't allow for our centroids to more flexibly move in the direction of new data points that were not necessarily seen in the first few batches. Okay. Any questions on that? All right. So we have a workaround if you'd like to try to use mini batch k-means more generally, in which you're not actually assuming that the mini batches are a random sample. And then the way that we can get around essentially, not encountering the situations in which the centroids become locked in place is we essentially add this additional centroid reassignment subroutine to the general mini batch k-means clustering algorithm. So basically, we use the same mini batch k-means clustering algorithm as we do here, but between the batch cluster assignment step and the centroid update step, we basically have this additional subroutine, which is sometimes activated and sometimes not. So what we end up seeing is if there is a particular, so basically after the batch cluster assignment step, if there's a particular centroid whose tally is comparatively a lot smaller than the largest centroid tally, then essentially what that suggests is that perhaps that centroid is not, it's not making the most of new potential observations that are coming in. So we might say, this centroid here, which hasn't had a whole lot of, observations, essentially being assigned to it, we might say it could be the case that that centroid might be better placed in the position of this new batch of information that has been coming in. So what we do, if this inequality, which uses this reassignment ratio parameter, so basically if this inequality holds for any given centroid's tally, then what we do is we free up that centroid. So we basically randomly reinitialize that given centroid to essentially, so we randomly assign it to one of our current observations in the batch. And then we reset its tally to be something close to zero. So either zero or something small, to essentially allow for that reassigned centroid to more flexibly move in the direction of the new batch observations that it has been assigned to. Okay, so let's take a look at an exercise, or basically the same data set, to see how the centroid reassignment subroutine might help. But before I do that, I wanted to give you guys about 30 seconds to check your email. So today will be our final checking Tuesday. So I do see that the emails have gone out. Okay, and I do believe everyone that has not been checked twice should have made it onto that list. So I'll give you guys a few more seconds to check your email and sign off if you need to. Okay. All right, so I'm going to assume that everybody is still here, was not selected, so we're going to keep going on. Okay, so let's just say we have this same full data set, again, that we would eventually like to cluster via the following 3 batches that are essentially fed into the mini batch k-means clustering algorithm. And let's just say we would like to use the centroid reassignment subroutine this time around. And we're going to use a reassignment ratio of 1/3. Okay, so our first batch comes in. It looks like this. And so we first randomly initialize each of our 3 centroids to be one of the observations in the current batch. Okay. And we would assign each of our observations to their closest centroid. Okay. And so basically, the centroid reassignment subroutine in the first batch is not going to be activated. And this is because each of the centroid tallies for each of my centroids currently are still set to 0. So we haven't actually assigned any observations, or we haven't actually updated the tallies for each of these centroids yet. So basically, the centroid reassignment subroutine doesn't come into play yet. But what we would do is batch 1 is, for each of the observations, update the tally of the centroids and update the cluster locations. And again, because each of these centroid tallies are, still currently relatively small, that allows for each of our centroids to much more flexibly move in the direction of the current point that is being incorporated in the cluster update step. Okay. And so we end iteration 1 with centroid tallies, which are relatively close in size to each other. So therefore, when we feed in batch 2, what we do next is we assign each of our new observations in batch 2 to their closest centroid. So most of these batch 2 observations are going to get assigned to centroid 3. And so then, after we've assigned each of our observations to their centroids, we check if the centroid reassignment subroutine is going to be activated. So now in this case, each of our current centroid tallies are in fact greater than or equal to 1/3 times the maximum of the centroid tallies, if you will. So basically, the centroid update routine inequality is not met. So basically, no reassignments would essentially happen in this step. So we simply just move on to the centroid update step for iteration 2. And now what we can see is that because there's basically all of the observations in batch 2 are getting assigned to the centroid 3, we're going to see much more of a disparity when it comes to the centroid tallies for centroid 3 versus centroid 1 and 2. Okay? So because of this, you can see that the centroid reassignment subroutine is actually now going to be activated when we move on to iteration 3, when we feed in batch 3. So when we feed in batch 3, again, what we can see is that each of these observations are, for the most part, closest to centroid 3. So therefore, all these observations would be more or less assigned to centroid 3. And then we would check our centroid reassignment subroutine again. And now what we can see is that actually the tally of centroid 2 is in fact less than 1/3 times the maximum of all of the current centroid tallies. So what that suggests is that perhaps centroid 2 might be, it might serve the overall clustering structure identification if it were allowed to essentially, move or essentially be reassigned to one of the observations in the new batch. So that's essentially what happens. So basically, centroid 2 is then randomly reassigned to, let's just say, like one of these observations here in the third batch. And then so when we move on to the centroid update step, each of these batch 3 observations will basically factor into the cluster update step. And because we have reset centroid 2's tally to 0, basically what that means is that this centroid 2 is now much more easily or much more flexibly able to move in the direction of the observations in this third batch here. So therefore, when we end the algorithm with our third iteration after incorporating our third batch, we can see that our 3 centroids are placed in much better locations than they were previously when, our previous centroids, over here were not allowed to essentially move, essentially. Okay. So basically by incorporating, just to summarize, so by incorporating this centroid reassignment step, it allows for your centroids to essentially be reassigned in a much better location for new batches, which may not necessarily have been showing the same clustering structure as the initial batches. So therefore, it allows for those centroids, which would have otherwise been much more locked in place in the location of the old batches, to essentially move in the direction of the newer batches, which may show a different clustering structure or pattern. Okay. All right. Questions on that? All right. And so, given that we're, if you choose to incorporate the centroid reassignment subroutine, then, that does add an additional parameter, i.e. the reassignment ratio that you would want to consider. So you'd want to consider like what a smaller versus larger reassignment ratio might do to your overall mini batch k-means clustering results. So let's think about what might happen if you set that cluster reassignment ratio to be a little bit lower. So if you set that reassignment ratio to be, relatively low, so let's just say maybe like, 1/1,000, something like that, then basically what that means is that you would have to wait for the algorithm to find, two centroids, let's just say, where for every one observation that was assigned to this, like the small centroid or the low count centroid, for every one observation that was assigned to that centroid, you would need about 1,000 observations to be assigned to your, to some other cluster centroid. So given that, do we think that, so if we set that reassignment ratio to be low, do we think that the algorithm would have to wait more time or less time to activate the reassignment ratio? So I'm going to post a poll here. So the question is, if we set our reassignment ratio to be low, do we think we'll have to wait more time or less time in the algorithm for that reassignment subroutine to be activated? Okay. Right, so try to submit in the next few seconds. Okay. Yeah, so most of us say more time. And so that is correct. Or in other words, we would have to feed in more batches into the algorithm in order for our clustering to even have a chance to experience a situation in which 1,000 observations had been assigned to one centroid in comparison to, like one observation being assigned to another centroid. So it takes more time for such a stark ratio to essentially occur when it comes to how many observations have been assigned to particular centroids. So what that means is that if you set that reassignment ratio to be smaller, then your centroids will not get reassigned as often. So you would, oh, sorry, I already answered that question. So given that, would we expect to see more or less cluster stability in each iteration of the algorithm? Okay, so try to submit in the next few seconds. Okay, yeah, right. So we would expect to see more cluster stability. And this is because, as we add more observations to a given centroid, well, if that centroid is not dramatically getting reassigned to some new observation, then we would expect the positions of these centroids to be, to change much more gradually, if you will. On the other hand, if it's possible in any given iteration for your centroid location to jump around to like new batch locations, then that's a signal that you're going to experience overall much less stability in terms of where your current centroids are, essentially. And therefore, you're going to experience much less stability with regards to what your clusters actually are. On the other hand, though, if you know that if your batches are not representative or they're not a random sample of the complete data set, then you may actually want to set your reassignment ratio to be large. And this is because, conversely, if you set that reassignment ratio to be large, then, for instance, you might need to only wait, for instance, to experience a scenario like this, in which, one of your centroids, for every one observation that has been assigned to your smallest cluster, there are just 2 observations assigned to your largest cluster. So this is a much much smaller ratio, if you will, between your smallest cluster versus your largest cluster, which is a scenario which is much more likely to happen. So therefore, it's much easier for the centroid reassignment subroutine to be activated, then the algorithm has to wait less time, i.e. feed in less batches, in order for the reassignment subroutine to be activated. So therefore, your centroids are more likely to get reassigned more often. And so because of that, you would expect to have less cluster stability in each iteration. Okay, but the thing here is, if you know that your batches are not representative or not a random sample of your full data set, you may not necessarily want to wait all that long before allowing for your centroids to move about in the direction of these newer data points. So even if you have the cluster reassignment subroutine, if you wait too long, then it's still possible that batches will be fed in that essentially don't allow for any centroids to be moved closer in that particular direction. So therefore, if you know that you'd like for the centroid or you'd like for centroids to be able to move more flexibly in the direction of less representative batches that are coming in, you might decide to purposely, create a larger or pre-select a larger reassignment ratio. However, there's also a downside to setting that reassignment ratio to be too high. So basically, if you set it to be too high, then the cluster or the centroid reassignment step is essentially going to be activated all the time in any given iteration. So for all intents and purposes, each iteration of your mini batch k-means clustering algorithm is going to essentially be starting from scratch. It's not going to be considering any of the information that it could have remembered about previous batches. So it's going to lose all of that information that the previous batches fed it. And so essentially you're just going to be like it's essentially like running k-means on each new batch that comes in, which is a waste of time essentially, because but then on top of that, you're losing valuable information from the previous batches that you might have wanted to have kept, essentially. Okay, so basically, if you're reactivating that, if you're activating that centroid reassignment ratio too much, then essentially what ends up happening is your clustering, your final clustering, basically only considers information from the final batch. Which is kind of like, what's the point? Like you could have just run k-means on just that final batch and essentially got the same results. Okay. So very quickly, just kind of put a pin in this. So yeah, so I just wanted to talk about some basic comparisons between mini-batch k-means and Birch. And so again, one of the benefits of mini-batch k-means in comparison to the non-online clustering algorithms is that, again, you don't actually need that full data set loaded in your Jupyter notebook to run the algorithm, which can be very beneficial if your data set is huge and it can't all fit in your Jupyter notebook. And a couple other things I wanted to talk about. If you're using these random batches, it's also possible that your mini batch k-means clustering results can actually converge more quickly than the regular k-means clustering algorithm can. And then some slight differences between Birch and mini batch k-means, because these are two online clustering algorithms that you could use. So you want to remember that Birch feeds in just a single observation into the CF tree at any given time, whereas mini batch k-means feeds in random batches of data at any given time. You also want to remember that Birch is actually, it's building that CF tree. So actually the data structure that is being built is, for all intents and purposes, a hierarchical, or it's a dendrogram essentially. So technically Birch is a agglomerative hierarchical clustering approach, which, as we've seen, can be prone to, like if you have a bad merge at the beginning of your hierarchical agglomerative clustering algorithm, that can actually lead to worse performance as you move up the tree. As we've seen, mini batch k-means is much more straightforward. It's much more explainable than Birch. Has fewer steps essentially. One of the downsides of mini batch k-means is that it doesn't actually take into account the memory limits that your particular computer might have essentially. But the nice thing about both Birch and mini batch k-means is that they actually have ways to go about detecting the overall clustering structure of your full data set, even when the first few batches of data fed into the algorithm are not necessarily representative. So you want to remember that step 4 of Birch allows for unrepresentative batches to be, essentially represented in the clustering structure. And then the analog to that in mini batch k-means is the centroid reassignment step. Essentially does the same thing. Okay. All right, I've gone way over, so I'm going to stop there. So that basically concludes at least what we're going to talk about for mini batch k-means. But like I mentioned, if you actually want to implement mini batch k-means, you can take a look at the application also in the zip file. Okay, all right, I'm stopping there. All right, so stop recording.